Hello everyone, welcome to NCERT Physics Simplified. From this video, I am continuing chapter number 6, work energy power. So far we have completed two paragraphs to this scalar product and the work energy theorem. Work energy theorem simply states that work done on a body is equal to the change in its kinetic energy. Okay, now let's understand work in this video. Okay, so article number 6.3 is work. Okay, as you know, work is simply the product of force and displacement. Okay, when a force is applied to a body and the body moves in the direction of the force applied, then work is said to be done. How it is calculated? It is simply the product of force and displacement. That will be the scalar product of dot product of force and displacement. Let understand it in more deeply from NCERT. Okay, so now as seen earlier, work is related to force and the displacement over which it acts. Okay, consider a constant force F acting on an object of mass m. The object undergoes displacement in the positive x direction. So now there is a object here. Okay, and we apply a force, constant force. Just remember, we later we'll talk about variable force, but for now we are considering constant force. So in real life, we apply a constant force on an object? Not necessary. Okay, more likely it will be a variable force, it will be changing. But for our understanding, let's understand work from perspective of a constant force. Okay, so a constant force will have a same magnitude all throughout. Its magnitude will not change. Okay, constant force is applied on this body, and you see the direction of this force is in this direction, making an angle theta with the horizontal. Okay, and because of this force, what happens? This object moves a certain distance in this direction, in the positive x direction. This is a displacement. Okay, so we can say that the displacement vector and the force vector is making angle theta with each other. Okay, now then, so work done by the force is defined to be the product of component of force in the direction of the displacement and the magnitude of the displacement. So how do we define work done by this force? So it will be the product of component of force. Okay, so as we know, how we have seen how to make components of a vector, rectangular component. Okay, so this component, the horizontal, the component which is close to the theta will be f cos theta. Okay, and this component will be f sin theta. So what we'll do for calculating work done, we will take this component. Okay, the component of force in the direction of the displacement, and this will, the product of this component and displacement will give us work, magnitude of work. Okay, so this is the definition of work. Okay, so now this is work is f cos theta times t, where this is a displacement. Okay, and this is nothing but the dot product or the scalar product. Okay, so now we see that if there is no displacement, there is no work done, even if the force is large. Very clearly you can see, if there is no displacement is zero, how much will be the work? Work will be zero. Okay, and you can increase as much, you can do as much work. If there is no displacement, there is no work done. Very simple example is pushing a wall. You can apply a large amount of force. Okay, but it will not move. Okay, the displacement is zero, so work done on the wall by you is zero. Okay, thus when you push hard against a rigid brick wall, the force you exert on the wall does no work, yet your muscles are alternatively contracting and relaxing, internal energy being used up, and you get tired. Thus the meaning of work in physics different from uses in everyday language. Okay, so this is very common example. Okay, you feel tired if you keep pushing a wall for a very long time. You will feel tired. Okay, your muscle are contract and relax, and your energy and be used up, but the wall has not moved, and because it had not moved, so in daily life, in daily uses, we may say that we have done some work in pushing the wall, But in the language of physics, it is not work, because there is no displacement. Only if there is a displacement by a force, then work is said to be done. Okay, another important point is that, so when is work is not done, there are certain points in this. Okay, first we have seen, if the displacement is 0, then the work done is 0. Okay, a weightlifter holding a 150 kg mass steadily on his shoulder for 30 seconds does no work on the load during this time. Okay, a weightlifter, if he holds 150 kg mass, okay, then for 30 seconds he will be feeling the force of that weight of the mass. Okay, then even though he is feeling the pressure, he has to just hold it for long, he will get tired. Okay, but because there is no displacement, he is just holding it, so he has, in physics language we will say, he is not doing any work. Okay, so this is the first case, displacement 0. Second point, the force is 0. If the force is 0, the work will be 0. A block moving on a smooth horizontal table is not acted upon by a horizontal force, since there is no friction, but may undergo a large displacement. Okay, so if there is a block, it is moving on a horizontal table. Okay, so since there is no friction, there is no horizontal force, so it is going a large displacement. It is moving on a smooth horizontal plane. Okay, so there is no horizontal force acting on it, there is no friction. Okay, so it is moving a large displacement, but the work is 0, because there is no horizontal force in this case. Now next, third point, the force and displacement are mutually perpendicular. If the force and displacement are mutually perpendicular, there is 90 degree between them. In that case also, the work done will be 0. For the block moving on a smooth horizontal table, the gravitational force mg does no work, since it acts at a right angle to displacement. We have seen that work done was Fs cos theta. If the angle between them, the force and the displacement is 90, then the work done will be 0. Okay, okay, now if we assume that the moon's orbit around the earth is perfectly circular, then the gravitational force does no work. Okay, so now the moon is moving in an elliptical path, you will see in the gravitation chapter, but let's assume it is moving in perfectly circular path. Then in that case, you see the work done by our gravitational force is 0, because the gravitational force is in centimeter, it is acting like a centimeter, which is acting on toward the center of the earth, and the moon velocity, let's take velocity, direction of velocity of moon at particular point, this is tangential. What is the angle between them? 90 degree. Okay, so there is no work done in this case also. Okay, so these were the three cases when there is no work: if the displacement is 0, if the force is 0, and if the angle between the force and displacement is 90 degree. Very common thing, very obvious thing that you have already studied earlier in your classes. Okay, work can be both positive and negative if theta between 0 degree and 90 degree, cos theta is positive. Okay, so if the angle between the force and displacement is between 0 and 90, then in that case work done will be positive. It is more than 90 and less than 180, that in that case cos theta will be negative, and that will be negative. An example of this is frictional force. You see a body is moving like this, okay, and the friction force is acting backwards, a positive direction of motion of the body. Okay, so what is it doing? It is trying to stop it. Okay, so it is acting opposite direction of motion, so this is example of a negative work. Okay, best example of negative work. Now from equation 6.4, it is clear that work and energy have the same dimension. Okay, we have seen work energy theorem, and we can conclude they both have the same dimension, that is ml2 t to the power minus 2. Okay, SI unit of work is also the SI unit of energy, that is joule, named after James Prescott Joule. Okay, Since work and energy are so widely used as physical concept, alternate units around the sum of these are listed. So the energy units are given, okay, like ERG, this is CGS unit, 10 to the power minus 7 joule, electron volt, okay. In atomic physics, nuclear physics, you will come across this. In semiconductor also, this is 1.6 10 to the power minus 19, okay. Uh, it is the energy possessed by a electron when it is accelerated in 1 volt potential difference, okay. So now then calorie, it is a earlier old unit of heat, it is around 4.186 joule. Then kilowatt hour used in electricity, it is called unit also. This is 3.6 into 10 to the power 6 joule. You should be familiar about of these units of work and energy, okay. Then after this we have this kinetic energy, very obvious topic, okay. So you know what is kinetic energy? Energy possessed by a moving body is kinetic energy, and you know what is the formula of this. This is half mv square, where m is the mass, v is the velocity, and kinetic energy is a scalar quantity, it cannot be negative, okay. So this is the measure of the work done. The kinetic energy of an object is the measure of the work an object can do by the virtue of its motion, okay. How much work an object, like a bowler throws a ball, okay. So how much kinetic energy it has, we can say how much work it can do, okay. That is the measure of the kinetic energy. This notion has been intuitively known for a long time. The kind of fast flowing stream has been used to grind corn, okay. So you know the fast flowing stream in villages, we use it to grind corns, okay. Now then sailing ship employ the kinetic energy of the wind, okay. You have must seen this, okay. The sailing ship, they have big flags, okay, and in these flags the winds exert force on this, and because of the kinetic energy of wind, the ship sails in the sea, okay. So now after this, the various kinetic energy of various objects are given, like car kinetic energy, okay. The mass is given, speed is given, half mv square. You can calculate this, how much is the kinetic energy of different object. And the real topics, that is for class 11th, it is this work energy, work done by a variable force, okay. This is the more realistic topic, okay, because in real life we are not dealing with constant force, we are dealing with variable force most of the time, okay. So from the next video, the real part of the chapter will begin, and this will be the work done by a variable force. We'll see in the next video, okay. Till then, thanks for watching. Do subscribe, share and like this video.